Hello, welcome to the online course on pericyclic reactions and organic photochemistry. We are in week number 6 and module number 25. We'll continue with the pericyclic reaction. This will be the last module concerning the pericyclic reaction. From module 26 onwards, we will concentrate on photochemical reactions. Now, ene reaction is a very important reaction in organic chemistry for the simple reason it involves two processes. One is a CH activation process, other one is a carbon-carbon bond forming reaction. Both CH activation as well as CC bond forming reactions are very vital to organic synthesis, and that is the reason ene reaction is an important reaction. What is an ene reaction? Let us first consider the definition of ene reaction. A reaction between an alkene bearing an allylic hydrogen, which is the ene component, and an electron deficient pi system, which is the enophile component, is the ene reaction. In this reaction, the allylic hydrogen is transferred onto the enophile with the concomitant formation of a carbon-carbon bond. The reaction involves a 6-membered cyclic transition state, very similar to a 1,5 hydrogen shift. So if you look at this example of a ene reaction, this is the alkene with the allylic hydrogen, which is this hydrogen that is shown here, and this is the enophile which accepts the hydrogen. So you can see here it involves a 6-membered cyclic transition state involving 6 electrons also, 2 of the CH bond electrons, 2 of this pi electron, and 2 of this pi electron. All of them in a cyclic transition state. This reaction undergoes the transfer of a hydrogen with the simultaneous formation of this carbon-carbon bond with the reorganization of the pi system towards the formation of this particular olefin. So you can see here the similarity between a 1,5 hydrogen shift. If you start counting from here, this will be 1 and 1. This will be 1, 2, 3, 4, 5. In the 1,5 hydrogen shift, there will be already a bond existing here. Here the new bond is being formed in this particular reaction. Instead of having a olefin, you can have a carbonyl functional group, and this would be called the carbonyl ene reaction. The product of a carbonyl ene reaction is a homoallyl alcohol, which is shown here, for example. This is a imino ene reaction, where an imine is acting as a enophile and the allylic hydrogen is transferred onto the nitrogen, resulting in the formation of a homoallyl amine kind of a product is what is formed. We'll see examples of each of this type in the due course of this particular module. The generalized ene reaction, of course, would be the one which is shown here, where you have an allylic type of a hydrogen available in a molecule, and typically this will be a alkene type of a molecule, whereas the enophile can be either an alkene, it can be an alkyne, it can be a carbonyl compound, it can be an imine, it can be a thiocarbonyl compound. Even singlet oxygen can behave like a enophile. We'll see some examples of such reaction. And finally, azo compounds can act as also as a enophile, resulting in the formation of hydrazine kind of a product. The highly ordered cyclic transition state of the ene reaction is shown here. Originally, this hydrogen is attached to the allylic system, so the HOMO of the ene is taken for consideration, which interacts with the LUMO of the enophile, which is shown in the bottom portion of this. So essentially the hydrogen is transferred onto this molecule. You can see here a suprafacial interaction is what is taking place. So it is a 2 sigma suprafacial, which is this sigma suprafacial, 2 pi suprafacial with respect to the pi bond here, and again with respect to this pi bond also it is suprafacial in nature. It is very similar to a 1,5 hydrogen shift, which occurs by a suprafacial shift under thermal condition. Ene reactions are always carried out under thermal conditions only. The negative entropy of activation is what is observed, corresponding to the proposal that it is a highly ordered cyclic transition state. About 30 calories per mole per 30 calories mole per Kelvin is the entropy of activation for this kind of molecules for the intermolecular reactions of this kind. An all-carbon ene reaction typically takes place at a very high temperature. In other words, it is very similar to a pyrolysis kind of a system, but more and more electron deficient groups are put in the enophile. In other words, electron withdrawing groups are being substituted on the enophile. The faster the reaction and the lower the temperature. We will see why that happens in a couple of minutes. If we consider the electronic effect of the intramolecular ene reaction, here is an example of a terpenoid kind of a molecule that is undergoing ene reaction. This hydrogen which is shown on the red is what is getting transferred onto this enophile with a concomitant formation of a carbon-carbon double bond resulting in a cyclohexane kind of a system here, and the olefin is of course rearranged to give the exomethylene olefin kind of a product in this particular case. When the enophile is substituted with the carbomethoxy functional group, the reaction takes place at a lower temperature with a higher yield. This is a very low yield of the product is what is observed under the pyrolysis condition, whereas under these conditions the yield is slightly better. Instead of one carboxylic acid functional group, when both the positions are substituted with the carboxylic acid functional group, the reaction temperature is brought down dramatically to about 180 degrees Celsius, and the yield of the product, ene reaction product, is also very high, which is about 75% or so. So this clearly indicates that in the enophile, if you have electron withdrawing functional group, as you make it more and more electron deficient, the reaction occurs at a lower temperature and the yields are also much better. This is essentially because the LUMO level of the enophile is brought down closer to the HOMO level of the ene component. So the HOMO-LUMO gap continuously decreases going from this molecule to this molecule which is substituted with the electron withdrawing functional group. Because of the closer nature of the HOMO-LUMO gap in the case of the electron withdrawing substituted enophile, the reaction proceeds faster because the activation barrier for this reaction is much lower than the activation barrier for the all carbon ene reaction of this type without any substituent. Now here is an example of beta pinene undergoing a ene reaction with maleic anhydride in one instance and with acraldehyde and acryl chloride in the next reaction, which is shown here. The hydrogen that is shown here is the one that is undergoing the ene reaction with the formation of a carbon-hydrogen bond resulting in the saturation of this double bond and forming a carbon-carbon bond between the maleic anhydride and the terminal position of this particular carbon here, resulting in the formation of the substituted maleic anhydride that is formed here. Here the reaction is regiospecific in the sense the hydrogen is transferred onto the alpha position and the carbon-carbon bond is formed between the beta carbon of the enone or the enoyl chloride and acetyl chloride and this particular carbon of the ene component of this particular system. Here is another example of limonene undergoing reaction. There are two double bonds in limonene. One is a disubstituted double bond, which is this double bond, which is a exocyclic double bond. It is a simple disubstituted double bond, whereas this is a trisubstituted double bond which is part of a cyclic system. So this is sterically more hindered compared to this particular system. So this molecule acts as the ene, this portion of the molecule acts as the ene component, whereas this portion of the molecule, because of probably steric hindrance of the triply substituted system as well as part of the cyclic system here, this does not undergo the ene reaction. When the reaction is carried out in the presence of acrylonitrile or methyl acrylate, the reaction regioselectively takes place from this particular carbon. This hydrogen is transferred onto the alpha position of the acrylonitrile or the acrylic acid ester, resulting in the formation of the carbon-carbon bond between the beta carbon and this particular carbon, methylene carbon, resulting in the chain extension that is shown here. So here is an example of a regiospecific reaction where the limonene undergoes the reaction only with the double bond which is not part of the ring system. The ring system double bond does not undergo the reaction under this condition. Benzene can very well be an enophile. This is an example of benzene undergoing ene reaction with beta pinene once again. The benzene is generated from orthofluorobromobenzene by treatment with magnesium. The halogen magnesium exchange, the Grignard reagent, is formed initially here, which undergoes elimination of the fluoride, resulting in the formation of the benzene as an intermediate. When the reaction is carried out in the presence of beta pinene as the trapping agent, trapping in the sense this is a ene component of this reaction, the hydrogen is transferred onto the benzene, resulting in the formation of benzene, resulting in also the formation of a carbon-carbon bond between this carbon here and one of the orthocarbons of the benzene in this particular instance. The reaction is carried out in refluxing toluene. So it's 80 degree, in about 62% yield this particular product is formed. So here the enophile is benzene and the ene component is the beta pinene, resulting in the formation of the beta pinyl substitute alpha pinyl substituted benzene derivative in this particular instance. This skeleton is alpha pinene, whereas this skeleton is beta pinene, for example. The regioselectivity can be very poor in the case of mono-substituted acetylenic or alkenic derivative of this kind. Here is an example of isobutylene undergoing reaction with methyl propiolate, for example. The reaction is carried out around 220 degrees Celsius. You can see here two regioisomers are formed. This hydrogen can be either transferred to the alpha position, which will give the major product, which is this particular product. The hydrogen can also be transferred onto the beta position, in which case this is the product that is being formed, which is formed in about 3% yield or so. The reaction is carried out at a much lower temperature, around 150 degrees or so, when the dimethylacetylene dicarboxylic acid is reacted with isobutylene, resulting in the formation of the hydrogen transfer from the methyl to this position, followed by carbon-carbon bond formation between this carbon and the olefinic carbon, which is the terminal olefinic carbon, resulting in the formation of this particular product that is shown here. Appol sir has devised a methodology to classify the ene reaction. According to him, there are 4 types of ene reactions that can be classified. The numbering system is as follows. You start with the numbering 1 from the position, which is allylic position, which is transferring the hydrogen, and end up with 5 to the terminal position where the hydrogen actually lands at the end of the rearrangement. Now the tethering group is, this particular group is what is connecting the enophile with the ene component. And this connectivity is, for example, between the third carbon of the enophile and the fourth atom of the enophile. This is the ene component third carbon, and the enophile component fourth carbon are connected by this tether. So the ene and the enophile are connected by this 4 CH2 methylene groups that are connecting this. That is the tethering group. On the other hand, if you look at this molecule here, the tethering group is connected to the second position of the ene component and the fourth position of the enophile. So it is called a 2,4 type. This is type 2. This is called a 3,4 type because it is a type 1, which the tether groups are attached to the third carbon and the fourth atom of the ene and the enophile respectively. Here if you look at, this is a 1,5 system because the hydrogen is transferred onto the Y position here, atom Y, resulting in the formation of a YXH bond. So this is the fifth atom of the cyclic transition state. The tethering group is attached to the fifth atom as well as the first carbon atom of the allylic system, which is the ene component here. If you look at this system, this will be a 3,5 system. This is a hydrogen which is going to be transferred onto this carbon here, resulting in the formation of a 6-membered ring in this particular case. So this corresponds to the 3,5 system. So these systems are essentially classified with this 2 numbers in the square bracket, which indicates the tethering connectivity of the ene component and the enophile component. The numbering starts from the allylic position, which bears the hydrogen, ends up at the position where the hydrogen is being transferred during the course of the ene reaction. The shortest route of the tether connectivity is for the 1,5 hydrogen shift is what these numbers are essentially indicative of this. And here you can have the XY group as either olefin, as carbonyl, or as imine, and so on, which we will see in a minute. Now here is an example of dihydrocarbon undergoing an ene reaction under pyrolytic condition, resulting in the formation of a 2,2,1 bicyclic ketone of this kind. So clearly this is the ene component here. This hydrogen is essentially this is the allylic hydrogen, that is, this is the enol form of this molecule undergoing the hydrogen transfer, the enolic hydrogen transfer onto this position, resulting in the formation of a carbon-carbon bond between this carbon and this carbon. So this has to undergo a both kind of a transition state in order for the connectivity between the dashed lines or the carbon-carbon bond connectivity and the hydrogen transfer connectivity. So the enolic hydrogen is transferred onto this position, and this carbon is connected onto the beta position of the enol in this particular case, resulting in the formation of a 2,2,1 bicyclic ketone, which is shown here. The transition state structure is shown in this particular structure within the square bracket here. Pericyclic compounds have been synthesized by ene reaction using this kind of a skeleton, carbon skeleton, where the ene component is clearly shown to be this particular component and the enophile component is this particular component, resulting in the formation of hydrogen migration in a 1,5 manner which puts this methyl group here because of the hydrogen transfer. This methylene becomes a methyl group here. You can see some amount of diastereoselectivity in terms of the formation of the cis and trans isomers of these two molecules. Here there are two reactions that is taking place. The first product that is formed is a major amount in 9:1 ratio. The major product is formed is the ene product. The ene product is arising from the hydrogen from this methylene transferred onto this position here, the alpha position, with a concomitant formation of the bond between these two systems. So this will be essentially 1, 2, 3, 4 kind of a type 1 kind of a ene reaction is what we are referring to here. And that takes place around 135 degrees Celsius. In 200 hours of the reaction, this reaction is taking place, for example. This product was formed, this is a byproduct. If you consider the carbonyl functional group and this double bond, this will be a Diels-Alder or diene kind of a system. So this will be a dienophile. So a 4+2 cycloaddition product is what is you can visualize as far as the product formation, which is a minor product concerned in this particular reaction. Lewis acids catalyze the all-carbon reaction, just like the Lewis acid catalysis of the Diels-Alder reaction and other reactions were discussed earlier. Coordination of the Lewis acids such as BF3 and aluminum chloride to the lone pair of the heteroatom of the enophile is what normally takes place. As usual, because of the electron deficiency being increased by the coordination of the Lewis acid, the LUMO of the enophiles are lowered in energy. So therefore the homo-LUMO gap between the ene and the enophile is reduced, and the rate is hence accelerated very much. Now imagine this reaction we already considered under thermal condition. The mixture of regioisomers are formed in this reaction. However, under the Lewis acidic conditions, only one regioisomer is formed. The other regioisomer is completely absent during the course of the reaction. That is not an important point here. The important point is the rate acceleration. The uncatalyzed reaction takes place around 220 degrees Celsius, whereas the catalyzed reaction in the presence of aluminum chloride takes place at room temperature around 25 degrees. So that is the most important aspect of this particular reaction. Similarly, in the case of acrylate also, regioisomeric products can be formed. However, under Lewis acidic conditions, only one isomer is formed, where the ene hydrogen is transferred onto the alpha position, and the beta position of the enophile is connected to the terminal position of the olefin, which is a ene component in this particular case. A carbonyl ene reaction is one where enophile is a C double bond O. So you can see here this hydrogen is essentially transferred onto the oxygen, resulting in the formation of a carbon-carbon bond, resulting in a homoallylic kind of a product. Essentially this reaction is equivalent to adding an allyl magnesium bromide kind of a reagent to a carbonyl functional group. So it is equivalent to that particular in terms of the product formation that is formed in this reaction, which is a ene reaction, carbonyl ene reaction, and this reaction, which is a equivalent reaction, which is a Grignard addition reaction. Essentially the equivalence is what is being shown by these two equations that are shown here. Formaldehyde is a very reactive enophile. Formaldehyde can undergo reaction with beta pinene in a ene reaction manner. The hydrogen from the allylic position is transferred onto the carbonyl, resulting in a CH2OH formation with a simultaneous formation of the carbon-carbon bond with the terminal position of the acid olefin, resulting in the formation of the homoallylic alcohol in this particular system. The same example is shown with chloral. Chloral is also a highly reactive enophile because of the electron deficient nature of the enophile. The trichloroacetaldehyde is more reactive than the formaldehyde itself. As you can see here, this is carried out at 180 degrees Celsius, whereas this is at a lower temperature of 95 degrees Celsius or so, resulting in the formation of a homoallylic alcohol system, which is substituted with the trichloromethyl group in this instance. Glyoxylates are also very excellent enophiles. The reaction is carried out around 150 degrees Celsius. In the case of hexamethylene cyclohexane, the product formed is the cyclohexene, which is substituted in the 1 position in this particular case, whereas alpha-methyl styrene is undergoing the reaction to give the alpha-methyl styryl derivative of the allyl alcohol, homoallyl alcohol of this product. In other words, this hydrogen is transferred onto the oxygen. A carbon-carbon bond is formed between this carbon and this particular carbon during the course of the reaction with the glyoxylate. So glyoxylates undergo highly regiospecific 1,5 hydrogen shift. The hydrogen shift is always onto the aldehydic oxygen. The aldehydic oxygen is a more reactive enophilic oxygen compared to the ester functional group, which is inactive in this particular instance. Here are some examples of intramolecular carbonyl ene reaction. In the case of this aldehyde, which is a terpene aldehyde, the reaction takes place at 180 degrees Celsius. A mixture of both the cis and the trans compounds are formed. We are talking about the relative stereochemistry between this carbon here and the newly formed carbon, which is this particular carbon, which is a stereo center. This can be either cis or trans. Both cis and trans are formed. The trans isomer is a major product, and between these two stereo centers it can be either alpha or beta depending upon whether the hydroxy is up or down with respect to the 1,4 stereochemistry. So the cis and trans refers to the 1,4 stereochemistry. The alpha beta refers to the hydroxy functional group being either alpha or beta with respect to the methyl group. So all the 4 possible isomers are formed. The trans beta is the major product in this particular case. In other words, the methyl group and the hydroxy group are cis with respect to each other, and the methyl group and the isopropenyl group are trans with respect to each other. Is the product that is a major product. When the reaction is catalyzed by zinc bromide, essentially predominantly only one product is formed. The trans isomer is formed. The cis isomer is absent in this particular reaction. In the trans isomer, the beta isomer is a major product formed in about 66% yield in this case. Here is a competition between a tri-substituted olefin and the mono-substituted terminal olefin, for example. Under normal thermal ene reaction, the sterically least hindered olefin is what is undergoing the ene reaction. The hydrogens from these allylic positions are transferred onto the keto diester in this particular case. However, when tin chloride is added, the reversal of the regiochemistry takes place. The hydrogen from this position is what is undergoing the ene reaction, resulting in the formation of a carbonyl carbon bond forming reaction at this position in a very high yield of 97.5% in this particular case. Chloral again can be catalyzed using aluminum chloride in terms of the carbonyl ene reaction. The two isomers that are formed, these are diastereo isomers that are formed. We will see in a minute how the diastereo isomers are formed in a ene reaction. At the time being, take it that the thermal reaction gives a particular diastereomeric ratio. The diastereomeric ratio is reversed when the aluminum chloride is added, essentially because in the transition state you can have either endo or exo transition state with respect to the ene and the enophile, which is reversed because of the aluminum chloride attachment to the carbonyl functional group. Lewis acid catalyzed intramolecular carbonyl ene reaction is shown here. This is a 3,4 type 1 kind of an ene reaction. Tin essentially coordinates to the oxygen of the carbonyl functional group, and the hydrogen from this methyl group is transferred onto the oxygen, resulting in the formation of a carbon-carbon bond between these two carbon, resulting in a cyclopentanols kind of a structure. Cis-trans isomers are formed, diastereo isomers are formed in about 80:20 ratio in this particular case. And this is an example of a highly substituted derivative being produced by a type 2,4 type of ene reaction. 2,4 connectivity essentially because this is the tether which is connected to the second position and to the fourth position, which is this particular position, because the fifth position is the one that is receiving the hydrogen in this particular case. So the hydrogen from this allylic position is transferred onto the oxygen. So this is 1, 2, and this is 3, 4, and 5. The 1,5 hydrogen shift is from this position to this position in this particular instance, resulting in the formation of an exomethylene cyclohexane derivative, which is highly substituted. In terms of the stereoselectivity of the reaction, this is highly stereoselective in the sense that this is the only product that is formed in about 100% yield in each of these diastereo isomers that are formed as starting material. The diastereo isomer in this particular case is a trans isomer, whereas here it is a cis isomer, giving a stereoselective product formation in terms of the diastereo selectivity with respect to this newly formed chiral center in this particular instance. Imino-ene reactions are the ones where the enophile component is an imine. Here a tosyl imine of the glyoxaldehyde is taken and it is reacted with cyclohexene, resulting in the formation of the product which is shown here by a transfer of a hydrogen from this position to nitrogen and resulting in the carbon-carbon bond formation to the beta position to give this product. This is a benzyl imine of aldehyde. Originally this was an aldehyde. The benzyl imine is formed, which is undergoing a Lewis acid catalyzed ene reaction even at room temperature, for example, resulting in the formation of a carbon-carbon bond between these two carbons here. The hydrogen from this molecule, from this position, is transferred onto the nitrogen to give the secondary amine, which is the benzyl amine in this particular case. Singlet oxygen is almost as reactive as benzene in terms of the ene reaction. Singlet oxygen can be produced under photochemical condition. In the photochemistry, we will see this once again, this particular reaction. When methylene blue kind of a dye is irradiated, it forms the excited triplet state, which transfers the energy onto the triplet oxygen, which is a normal oxygen, producing the singlet oxygen in the process. The singlet oxygen is essentially as O double bond O kind of a configuration is what we have. So this is essentially the hydrogen is transferred onto the oxygen, and there is an oxygen carbon bond is formed, leading to the formation of peroxides. So here again the beta pinene derivative is undergoing a singlet oxygen ene reaction to produce the corresponding hydroperoxide in about quantitative yield in this particular case. We will see more examples of the oxygen ene reaction in the photochemical reaction when we consider singlet oxygen reaction. Now we will explain the origin of diastereoselectivity in the ene reaction. Remember, early on we saw the formation of diastereoisomers in the ene reaction. What causes the formation of selectively one or the other diastereoisomer in a ene reaction is explained here. There are two transition states that are possible. The hydrogen, the X group in the enophile can be endo with respect to the ene, or it can be exo with respect to the ene. Here you can see here the CX bond is exo with respect to the ene. The CX bond is endo with respect to the ene. The hydrogen is transferred onto the beta position here, with the concomitant formation of the alpha position with this particular carbon here, resulting in the formation of these two products. This product is similar to a trio kind of a product, whereas this is similar to an erythro kind of a product. So the transition state is what is clearly shown here. The X is exo to ene, X is endo to ene. That will result in the carbon-carbon bond formation, resulting in the diastereomeric form. If the endo isomer is a favorable transition state, endo transition state is a favorable transition state, this will be a major product. If the exo transition state is a favorable transition state, then this will be a product. It would depend upon the bulky nature of the X group. It will also depend upon whether X is coordinated to a Lewis acid and so on. So there are several factors which are involved in the reaction. Normally, if you consider the all thermal ene reaction without any kind of a Lewis acid catalysis, it seems that the endo ene reaction is the most favorable reaction. Perhaps there come some kind of a secondary orbital interaction between this carbonyl and this carbonyl over here, resulting in the formation of this as a major product. The minor product, which is shown, is formed only in about 20% yield, arising from the exo type of a transition state in the ene. These are examples of the diastereoselectivity in the ene reaction. When methyl glyoxylate is used as the ene product, enophile, and cis-2-butene is used as the ene component, the diastereoisomers are formed in about 7.5:1 ratio. This is the thermal reaction. Uncatalyzed ene reaction is what is shown here. When you do a catalysis using either tin chloride or methyl triplet, depending upon the Lewis acid catalyst, the regioselectivity is changed, the stereoselectivity changes. For example, when tin chloride is used, 2-butene is used or cis-2-butene is used. The product that is formed here is the major product, which arises from the endo selectivity. Whereas when 2-butene, cis-2-butene or trans-2-butene is used with the methyl triplet as the Lewis acidic reagent, the product arising out of the exocyclic transition state is what is a major product in this case. So the diastereoselectivity can be explained by looking at this picture here. With the bulky group, if it is attached to the X group, for example, by Lewis acid catalyst, this may be a crowded transition state, in which case this is a preferred transition state. Normal thermal ene reaction, probably this transition state is favored, and that is why that particular diastereoisomer is formed as a major product. In the process of generating the ene reaction, you also generate chiral centers because of CC bond forming reactions that are taking place. So one can also imagine a asymmetric ene reaction. In this particular case, this pendant group is attached as a auxiliary to the glyoxylate. In other words, the glyoxylate ester is a chiral ester arising from a menthol kind of a derivative in this particular case. Ene reaction produces the diastereoisomer in 99% yield. Once this is cleaved, the particular enantiomer will be formed in 99% yield. So this is a Lewis acid catalyzed, not catalyzed, this is almost stoichiometric amount of Lewis acid is taken, because in the product also you have oxygens present, so the Lewis acid will be tied up to the product oxygens also, and that is why excess amount of the tin chloride is taken, although the role of tin chloride is only catalytic in this particular instance. Here is an example of alpha phenyl cyclohexanol, which is an optically pure compound, which is esterified to the glyoxylate ester is formed in this particular case. This is a chiral auxiliary, so it used for inducing the chirality for the newly generated chiral center that is formed. The Yin reaction, essentially this hydrogen is removed, transferred onto the glyoxylate oxygen here, resulting in the migration of this double bond over to this position, forming this particular product. This is a starting material for a natural product called specionin. So this is essentially stereoselectively synthesized by an asymmetric transformation by generating these two chiral centers simultaneously during the course of the reaction by taking a chiral auxiliary in this case. Lewis acid catalyzed asymmetric Yin reactions are also known. This is a chiral Lewis acid is generated by reacting the methyl aluminum chloride with R-binol. Binol is an optically active diphenol. When aluminum chloride reacts with the binol, the corresponding aluminoxy derivative is aluminum phenoxide derivative is what is found. So that undergoes the Yin reaction. This is the Yin component with allylic hydrogen, and this is a enophile, which is an electron deficient enophile because it is a pentafluorobenzaldehyde, which is a highly electron deficient aldehyde. The efficient Yin reaction takes place even at minus 78 degrees Celsius, resulting in the formation of enantiomerically pure one isomer of this formed because of the chiral induction from the R-binol results in the chirality in this particular position. So here this is an example of a chiral Lewis acid catalyzed asymmetric Yin reaction. Another example of a chiral Lewis acid catalyzed Yin reaction is using titanium isopropoxide and binol. Here the titanium isopropoxide essentially exchanges with the binol to give the binol titanium enolate kind of a product is what is formed. Methyl glyoxylate is the enophile, and the alpha methyl styrene is the Yin component, resulting in the formation of 97% chemical yield of this compound with 97% enantiomerically pure homoallylic alcohol is produced in this particular instance. So what we have seen in this particular module is a very important reaction, which is essentially a 1,5 hydrogen shift kind of a reaction taking place either intermolecularly or intramolecularly, and it is classified as the Yin reaction. And the carbonyl Yin is the one where the carbonyl group is used as the enophile. There are two components in a Yin reaction, the Yin component and the enophile component. The Yin component is invariably a compound having an allylic hydrogen. The enophile can be either carbon-carbon double bond, carbon-oxygen double bond, carbon-nitrogen double bond, a variety of Yin reaction we have seen. The asymmetric version as well as the diastereoselective nature of the Yin reactions are explained in this particular module. I hope you enjoyed this module. Thank you very much for your kind attention.